This is from the Force Vectors lab. We've got several scenarios where we're doing the concept of action-reaction. We're doing these with static equilibrium systems where there's no overall movement, but we've got several forces involved. And we're trying to see how they act and react against each other based on their components, X and Y components. So one of the systems you had looked, let me just do a quick sketch here. We have an unknown mass hanging, and it might have been, it might have been the blue donut, and there was 200 grams over here, and then over on this side, hanging over another pulley, were a couple of these weights at 400. That's 200 and 200, so we had 400 grams over here. From the horizontal, you remember you measured this with your phone, so you put your phone alongside of here and you were able to measure the angle in it, and the angle it typically measures is right here. So one of the angles, for example, might have been 71 degrees. I'm using some data that I recorded in this, 48 degrees. Now this isn't drawn to scale, but I approximated the angle. Okay, let's do the free body diagram. To do the free body diagram, we want, first of all, we want a nice straight line, horizontal axis. And then to get the vertical axis, I'm going to get that 90-degree line lined up, and there's my axis. Okay, so this is going to be, as our free body diagram, we represent this point right here with this dot. This is where all three forces are acting at that one central spot. Going down, we have an unknown mass. Now I don't know, always use the centimeter side. I don't know how far down that's going to go, but it's going to be in that direction. And that's the unknown. So that's our goal, is to figure that out. Determine the mass of the unknown. I do know that this angle is 48 degrees, so let's go ahead and do this to scale. Line things up carefully. 10, 20, 30, 40, and 8. And the magnitude, well, this is over here. Let's do this in newtons. So over here, I'm going to go ahead and calculate this weight down here. Scooch this over. So this is F equals, this is a weight, but it's going to be treated as a tension force right here. So that's mg. The F, force due to gravity, is the weight, equals mg. The mass is 0.200 kilograms, and g is 9.81 meters per second squared. 0.2 times 9.81, 1.962, 1.96 newtons. And we'll do the same thing down here as well. .400 kilograms times 9.81 meters per second squared, which will be twice that. So we're looking at 3.92 newtons. So that means that at this 48-degree angle, I have a force of 1.96 newtons. 1.96 is pretty short. I'm going to go ahead and double this scale. So my scale is going to be 1 newton is equal to 2 centimeters. So I'm going to double that, and that'll be 3.92. So I'm going to line up my 3.9, give me a little bit of a 2 there. Let me just draw the line first so I can then get the measurement down. So I'll draw that lightly. And then 3.9, I'm putting the 3.9 right on the line, or right on the dot. And now I'm going to draw my vector to the 0 spot. And then carefully draw my arrow as to not extend that. So this angle is 48 degrees, and that is 1.96 newtons, but when measured it was 3.92 centimeters. And then over here it's 71 degrees. Ten, 20, 30, 40, 50, 60, 70, and 1. We have, draw that in. This is 71 degrees. And that is 3.96, yeah, 3.92 newtons, which is 7.84 centimeters. So that's taking us up here near the top. Whoa, I'm almost off the sheet here. I think I am a little bit off the sheet. I could have put this down a little bit. That's okay. We're going to do it anyway. All the way up to the top. It's really just a little bit off. That's okay. We're doing this mostly based on calculations, so that'll be all right. So that is 3.92 newtons, which was measured at 7.84 centimeters. This is the action-reaction stuff. So we're going to break this up into two components. So this is going to be, I'll call this F1, and we'll call this F2. And F1 Y, because it's in the Y direction. And F1 X. Put a dotted line in here. I'm kind of moving it a little bit off of the axis so you can see it. That's F1X. And then this is F2. I'm getting it parallel to the axis. So that's F2 in the Y direction. And this is F2 in the X direction. And we can already see that the F1X and the F2X are just about equal and opposite, just by visual appearances. We'll see how the numbers work out in a second. When we calculate the adjacent angle, it's equal to the hypotenuse times the cosine of that angle, theta. The hypotenuse is our 1.96 newtons, and our angle is 48. And over here, the same thing, adjacent equals hypotenuse times the cosine of our angle. Our hypotenuse over here is 3.92 newtons. And our cosine of our angle is 71 degrees. So, let's see what we have with those two. 1.96 cosine 48 is 1.31. And given the magnitude of this length, 1.31 looks reasonable. And since it's going in this direction, it is, to the left, we will consider this to be negative. And then over here, 3.92 cosine 71 is 1.28 newtons, and that is in the positive direction. So notice the negative 1.31 and the 1.28. Pretty darn close, right? 1.3, 1.3 when you round it. So those are pretty good. Now, those cancel each other out in the horizontal direction. These two forces right here going up are going to cancel out the weight of this object going down. So we can predict the weight of this vector right here. We can predict the length of this vector, which represents the weight of our unknown. So this is the force of our unknown, F-U-N, fun. And we base it on these two. So this is an opposite leg. So opposite equals the hypotenuse times the sine of theta. Hypotenuse again, 3.92 on this side. 3.92 sine 71 is 3.71 newtons. And that is in the positive direction, up. And over on this side, the opposite leg equals the hypotenuse times the sine of theta. And the hypotenuse is 1.96. And sine of the angle 48 degrees, 1.96 sine 48 is It's 1.46. That is also positive because it's going up. So the unknown is going to be equal and opposite to the sum of these two forces right here. So the net force, we can think of it this way as well. We can say the net force, the sum of all the forces in the y direction has to equal 0. And the sum of all the forces in the y direction is F1y plus F2y minus the force of the unknown. The force of the unknown is in the negative direction, so I put minus. Anyway, that has to all equal 0. And so that means the force of the unknown is equal to F1y plus F2y. That is 1.46 newtons plus 3.71 newtons, which is 1.46 plus 3.71 is 5.17 newtons. If we want to know what the mass is, we then divide that by g, right? F sub g equals mg. The mass is equal to F sub g over g. So that's our weight, 5.17 newtons divided by 9.81 meters per second squared. And that is 0.527 kilograms, 527 grams.